So we've spent the past couple of units talking about forces and their effect on acceleration using Newton's second law, net force equals ma. There's some other ways to think about how forces can affect motion, and these other ways can sometimes be more helpful if the forces are complex and harder to study. And one of those ways is the topic of momentum, which we've just started to discuss in class. So by keeping track of something's momentum and how it changes, we can actually learn a lot about force. And in this video, I would like to use this scale as a way of measuring force. As I press it, it reads more and more force. And I've got this massive object here, which is one of the rollerblade wheel carts full of textbooks. So I'm going to be giving pushes to the cart. And you'll be able to look on the scale needle to see how hard I'm pushing. In this first trial, I'm going to push with a relatively small force, about 2 pounds. I'm going to do it for a count of 2 seconds, or at least a count to 2. 1, 2. In this trial, I'm going to push with that same small force, 2 pounds, but I'm going to do it to a count of 4. 1, 2, 3, 4. So we're going to describe what we just saw in terms of this new concept of momentum. So momentum, as you've learned, is how hard it is to stop something. It is mass times velocity. And we're going to look at how momentum changed as I pushed the cart in those various ways. So when you see here delta mv, that means change in momentum, and it just means momentum final minus momentum original. We're going to give it another name, which is impulse, which is abbreviated J. And as you could see, I gave the carts various different impulses. At first, I gave the cart a very small impulse because I pushed with the small force of about 2 pounds for a very short time, a 2 count. I then gave a larger impulse by pushing with that same 2 pound force, but for a larger time, a 4 count. Is there another way I could have increased the impulse? Absolutely. I could have increased the force. Let's give that a try. In this trial, I'm going to push with a force of 8 pounds for a 2 count. 1, 2. So apparently, if you want to change something's momentum, you have to consider both force and time. We saw that when I had small ones of both of those, we had a small change in momentum. If I wanted to make it bigger, I either had to push for a longer time or I had to push harder. It may not seem that this is very interesting. Before we were relating forces to accelerations, now we're relating forces to changes in velocities. It just seems like more math for the sake of math. But this is actually a much more useful way to learn about forces that are complex. Check this out. So, in reality, the change in momentum is not just F times t. It's actually the area under the curve on a force versus time graph. And that's this maroon area here. Now, that looks strange. But the reason this area under the curve is so important is before we've only really dealt with constant forces. This is clearly not a constant force. It's small, it increases to a peak, and then decreases back to small. This is actually the force you get when a tennis ball bounces off the ground. As the ball is coming into the ground, it starts to smush, and the more it smushes, the more force there is. Here's where it bounces back up, and it gets less and less smushed, and it leaves, and the force goes to 0. How would we describe that using sigma F equals ma? There's no room for time dependence in that equation. So using this way of describing force and getting the area under the curve to figure out how momentum changes It lets us deal with the non-constant forces. Now, we just kind of saw that change in momentum was approximately force times time. Where does that come from? Well, imagine that this is the force describing a bouncing tennis ball. And imagine all I could get was the change in momentum of the tennis ball. I actually don't really have to know about this force. I could pretend that there was a constant force, this orange one. It wasn't as high as the peak force, it wasn't as low as 0, but the area under it was the same area as the area under this one. Both of those areas will therefore be equal to my change in momentum. So why would I do that? Well, this force is kind of like an average. It's not the lowest, it's not the highest. But the area under this curve is really easy to get. Length times width, force times time. So force average times time is the change in momentum. That's what we saw before. In all of the physics classes except for AP, we're going to use this idea that change in momentum is equal to force average times time. That'll be the equation we use. In AP, we actually will deal with this area and how you get it. You use a technique in calculus called taking the integral, which is what this means right here. And you'll get to it when you take calculus. Isaac Newton actually wrote his second law not as sigma F equals ma, but using the concepts of momentum and impulse, because it gave him this ability to deal with non-constant forces.